fundamental theorem of calculus part 1 says if little f of x has an antiderivative, it's big F of x. And what we did yesterday was to recognize that, hey, that's a really cool way of doing the area. So we can do the area between A and B is given by the formula f of B minus f of A. Now notice that big F of x is the antiderivative of little f of x, and f prime of big F of x is little f of x. That's the relationship that we need to. You can. They're not opposites of each other, and they're not inverses of each other. But what one does, it's sort of like what one does, the other one undoes. You know, kind of that kind of thinking. Yes. Yes. The derivative of the antiderivative is the function itself, which is what you just killed my entire lesson. But that's basically what we're going to learn today. The derivative of the antiderivative is the function itself. Yeah, okay, and now we'll do section 9. Yeah. Well, it gets a little bit more technicaler. Yeah, kind of, yeah. Okay, so consider the antiderivative between 0 and 3 of 2x dx. So what we did yesterday is we took the antiderivative of 2x and we said it was x squared over 2. No, yeah, 2x squared over 2, so it's just x squared plus c. I got lazy. 0 to 3, and we would go 3 squared plus c minus 0 squared plus c, and we all went, why are you still writing down the c's? And we got 9, right? So the area under that curve is 9. But what I want you to do is to identify what little f of x is and what big f of x is. So you will do this, you go, there's little f of x, and you go, and there's big f of x. Yeah? Now the fundamental theorem of calculus can be stated another way. You're going to look at it and go, what? Why would you write it like that? Well, we could also write it like this, which is equal to this. Which is equal to this. Gotta love the capital, lowercase, capital, lowercase. You gotta be careful. Okay. Well, why? Well, there's another theorem. Well, there's one other form of the fundamental theorem of calculus, also called the second fundamental theorem of calculus, or the fundamental theorem of calculus part 2, or the fundamental theorem of calculus redux. I don't know. Anyways. The derivative of the antiderivative. Hate when people ruin my lessons. The derivative of the antiderivative from a to x of f of t dt is, well, we're going to pretend that we didn't hear that statement way back at the beginning. d dx of the antiderivative f of t from a to x equals the derivative of f of big F of x minus big F of a And then you look at it and go, well, this is silly, but I'll write it down. The derivative of big F of x minus the derivative of big F of a what's the derivative of big F of x? Little f of x. What's the derivative of f of a? 0. It's a constant. Here's the rule. Is the function itself. It's the function that you started with. Because we switched variables. We switched from t to x. We switched variables from t to x. But it's the same function. Mr. F, I don't believe you. Say it. Say it. I don't believe you. Good. Thank you. Okay. So we pretend that we still don't believe you. Not proof. This is just evidence. A better way of saying this is evidence. I'm not about to prove the second fundamental theorem of calculus. I don't want to. So the antiderivative of t dt is 1/2 t squared plus c, and we're going to evaluate that from 1 to x. Substitute in x, you get 1/2 x squared plus c minus 1/2 1 squared plus c. What happens to the c's? Good. 1/2 x squared minus 1/2 times 1 squared. Okay, what's the derivative of 1/2 x squared? X. What's the derivative of 1/2? 0. Leave me yet? So what's the next one going to be then? What's the answer going to be? Thank you for not being very confident. 3x squared minus 2x. Do you want to do it? Do you want me to do the process above that we just did above, or just, Mr. F, if I see this, I already know the answer. Okay. What's the next one then? What's the next one then? Okay, be careful for this one. This is a T. and it's dx. So we're switching from x's to t's now. Oh, where's the 5 coming from? Not hard, is it? No. Oh yeah. Sucker. Okay, so notice that the last day rules developed from the end of the lesson. Okay, so for those people who were here yesterday, they can kind of say, oh yeah, right. Okay, so most people say sine cubed x and get sucked in because it's wrong. Because it's out of order. And whenever you color out of order, it's negative. Remember, we learned in art that we must color from left to right and stay inside the lines. Go tell Mrs. Yamoka that. We always color from left to right, and we stay inside the lines. There will be no coloring from right to left. None whatsoever.
So you actually there doesn't one that comes back?
Yeah. Yeah.
There won't be like two dots.
No. That's just me. Okay, so what happens when it's not x? Or sorry. Lots of us would like to just say x, but we got to be careful, so we're going to start at the beginning again with this one. Because the variable isn't x up top, it's x cubed. Okay, so starting again. The antiderivative of t dt is 1/2 t squared plus c, and then we're going to evaluate that between 1 and x cubed. So one half x cubed squared plus c minus 1/2 1 squared plus c. So the c's cancel again, and what we have to do is the derivative of each of those parts. Now, when I was making the notes up for this last night, because I didn't remember the second fundamental theorem of calculus until I reviewed it. Went, oh yeah, right, that's all it is. I went x cubed squared is x to the 6th, and went at it from that. It actually makes the rule that we're trying to generate not easy to see. So I'm asking you to not remember your exponent rules for a second. To say I don't want you to go x cubed squared is x to the 6th. I just want you to see it as x cubed squared and use the chain rule to take its derivative. So drop the 2 down out front. So it's 1/2 times 2 x cubed to the 1 times the derivative of the inside. Times 3x squared. Okay, we're going to clean that up just a little bit. It doesn't seem to make logical sense to do it like this, but you just trust me. Those cancel, and you're left with x cubed to the 1 times 3x squared. Take a look. Take a look at this piece. And take a look at this piece. Ooh, say it a little louder, my friends. Yeah, this is, okay. So if this is u, we need to multiply by u prime. What's the gray part? Yeah, it's f of u, yeah. It's the chain rule. Again. Derivative of the outside times the inside, except for it's not the derivative of the outside, it's just the outside changing variable. And you have to remember to multiply by the derivative of the inside. But if I went x cubed squared, if I actually wrote that as x to the sixth, you wouldn't have seen what had happened. It would have been harder to see what had happened. You can see the two pieces there now? Yeah? So when the upper bound of the integration is not just an x, if it's an x squared or a sine, like an x squared. So it's going to be sine x squared times 2x. This one's going to be, this is the new function. So what's this one going to be? 1 minus, well, I was going to not do it too fast, x cubed squared times 3x squared. So it becomes 1 minus x to the sixth. Hard? You just got to be careful when the variables are not just x. If it's x cubed, you got to go, oh crap, I got to do a really weird version of the chain rule. Okay, what about this one? Yeah. And then you can clean it up because the x cubed and the x to the fourth in the denominator clean up. So you're left with 4 cos x to the fourth over x. What about the next one? Times. No. It's just the derivative of this. And you're done. I don't know where that one is, so we'll just not put that one there. Okay, oh crap. Being mean. Negative. Because we're doing it out of order. Root. I'm just going to dance along. No, you always do the one with the variable, dear. So that's Dylan's question. Will there ever be two variables? Dylan, have you figured out the answer to the question yet? You don't. Well, if you do, if there are two variables, if there's x and then x squared, then you're going to do it separate. You have to do it old school, long-winded, do it like it's a normal problem, and then take the derivative of each piece. Okay. F of big B minus F of big A, yeah. Okay. Sometimes they test the second fundamental theorem of calculus in a devious way by considering an area function, A of x. Let A of x be the area from 1 to that number x. Well, what does this mean graphically? Well, what it means graphically is this. So we have a bit of a parabola. What we're doing here is we're making a function that gives the area of the parabola as we pull that edge of the parabola farther and farther away. So a of 1 is the distance. This one you don't actually need to write it down, but we'll write it down. The area between 1 and 1 of t squared dt. No calculation required. How far apart are the net numbers 1 and 1? 0. So what's the area contained? 0. Okay, a of 2. Well, that one requires some work. So the antiderivative from 1 to 2 of t squared dt. So we take the antiderivative, 1/3 t cubed plus c. And you substitute 1 in, you substitute 2 in. Oh, sorry, you substitute 2 in first, so 2 cubed plus c minus 1/3 1 cubed plus c. So 8/3 plus c minus 1/3 plus c, and you end up with 7/3. A of -1. Well, the nice thing is you can skip. You don't have to skip steps, but you definitely know what the next step's gonna be. Well, what I would just do, sure, it's also the antiderivative between -1 and +1 of negative t squared dt. Yeah, I'm running out of room. So then you just clean it up. C's cancel. You're left with one-third plus 1/3. So the answer is negative 2/3. Yeah. Yeah. Yeah, you don't actually need to flip the order and put the negative in front. You could actually do it. Yeah. That's right. Yeah, it's just we tend to like to color. We learned in art that we always color from left to right and stay with inside the line. Okay. Well, what's a prime of x? Well, that's the derivative between 1 and x. What was the area function, t squared? Okay, we'll jump to the answer. You know that. No. X squared. So what's a prime of 3? What's the next one? 4. Now what does this mean? This means how fast is the area increasing when x is 3? It's increasing at 9 units per time. 9 square units per time? How fast is the area? Yeah, 9 square units per time. There you go. That is the second last section.